In a distant galaxy called NGC 7727, two supermassive black holes are slowly spiraling toward each other, a cosmic dance that will end in one of the most powerful events in the universe. Tonight, we'll explore what happens when giants collide. If you enjoy journeys like this, please like, subscribe and share, and tell us in the comments, what do you think will happen when these black holes finally merge? Thank you for watching. Now, let's begin. Far beyond the reach of the Milky Way, a quiet portion of the universe opens within the constellation of Aquarius. Across this deep expanse, light moves slowly and evenly, spreading from galaxy to galaxy in long, unbroken lines. The scene holds no sound, no turbulence, only a faint shimmer where distant systems drift. Among these islands of stars lies one particular remnant, a faint and asymmetric shape known as NGC 7727. It rests about 89 million light-years away, appearing to the eye as a softened oval with uneven edges. Around it, thousands of other galaxies form a subtle web, their collective gravity balancing expansion with attraction. From this distance all seem calm, yet beneath that calm lies motion, too vast and slow to sense directly. In the greater field, galaxies appear as smudges of light, each the combined glow of billions of suns. Most follow familiar pattern spirals with clean arms, ellipticals with smooth halos, irregulars with scattered clusters. The remnant in Aquarius, however, stands apart. Its outer shape is broken as though torn and reshaped by ancient forces. This distortion marks the memory of collision, the quiet outcome of two galaxies that once crossed paths and gradually became one. Through telescopes on Earth, its faint arms and displaced core reveal an origin of turbulence long subdued by time. What remains now is a system settling into balance, its luminous dust and stars wrapped in a field of silence. The surrounding space is almost empty, yet never void. Between the galaxies stretch threads of gas and dark matter, invisible but real, guiding the slow drift of systems through cosmic time. Each thread bends light imperceptibly, a reminder that even darkness has structure. The remnant in Aquarius moves within one of these filaments, part of a larger association known as the Cetus Aries group. Within this cluster, mutual gravitation draws galaxies toward one another, while the overall expansion of the universe carries them apart. For now, equilibrium holds. The distances between members change so slowly that from any single lifetime the field appears frozen. Light from the remnant travels nearly 90 million years before reaching modern instruments. What is seen today is an echo of what once was a record, not a present state. The photons, now caught by mirrors and sensors, began their journey when mammals were still small and scattered on a younger Earth. Each beam crosses a gulf of space so large that even light, the fastest traveller known, ages as it moves. The image that arrives is gentle and pale, its structure blurred by the scale of its own distance. Observers see not an active collision, but the aftermath of one long past. From this vantage, the galaxy's outer halo blends into the background. Stars once confined within spirals have been thrown into arcs that extend far beyond the core. These tidal streams are faint but measurable, forming graceful loops that encircle the remnant like memory traces of motion. They record the gravitational tides that once stretched and folded two galaxies into a single irregular form. The faint glow around the object shows that its stellar population is old. Blue light has faded, leaving the warmer hue of mature stars. In the central region, however, the light is denser and slightly offset, hinting at the complexity hidden within. Elsewhere in the same field, smaller galaxies drift like silent witnesses. Some are companions, possibly remnants of the original pair now drawn into new orbits. Others belong to more distant backgrounds, mere coincidences of line and sight. Together they frame the object's position in space and mark the scale of its surroundings. The intergalactic medium between them is thin, only a few atoms per cubic meter, but it binds the scene together through gravity. In that tenuous web, matter flows gently toward deeper wells of mass-feeding systems like the one now observed. From Earth, NGC 7727 shines faintly in long exposures, yet through advanced instruments it reveals intricate layers. Optical telescopes show its distorted structure. Radio arrays trace the remaining gas. X-ray observatories detect the energy of its central regions. When all are combined, a portrait emerges, a quiet galaxy, still carrying the scars of an ancient merger. Its light is steady now, but the paths of its stars remain unsettled, moving in slightly irregular orbits that reflect a history of disturbance. These motions persist for hundreds of millions of years, slowing only as gravity smooths the last uneven edges of the collision. In this wider cosmic view, the galaxy field acts as a calm ocean on which the remnant drifts. Each system upon it is a vessel of stars and gas bound by its own mass, yet influenced by the pull of its neighbours. Space itself expands, carrying the galaxies apart, but local gravitation sometimes overcomes that motion, creating new encounters. Such meetings are rare, yet inevitable in the long history of the universe. The present calm hides the evidence of those ancient moments when light and matter collided, reassembled and cooled. Beyond the remnant's faint outline lies the true silence of intergalactic space. The background glow from the first light of the cosmos still lingers just under 3 degrees above absolute zero, evenly filling every direction. Against that dim radiation, each galaxy stands as a warmer flicker, proof that matter can gather and shine even in a universe that tends toward stillness. The field is vast and nearly motionless, but within it gravity continues to work with quiet precision. Stars age, galaxies drift, and light records the passage of time without pause. From this outermost perspective, NGC 7727 is no more than a single blur among countless others, but its light carries a story written across eons. What now appears tranquil was once an event of cosmic scale, the meeting of 2 full galaxies whose cores have not yet completely merged. Their aftermath glows softly against the black. Across the millions of light-years that separate observer from object, this remnant of violence appears perfectly calm. It floats amid a sea of galaxies, its shape slightly uneven, its halo faint but persistent. The field around it is so still that it feels outside of time, a steady framework upon which the rest of the narrative will unfold. Within that equilibrium, the system continues its drift through Aquarius, an ancient luminous scar suspended in an ocean of darkness, holding within its depths a hidden motion yet to be revealed. In the wide sky of Aquarius, the galaxy stands as a survivor of collision. From Earth it appears faint but distinct, its form neither spiral nor elliptical, but something in between. The image is slightly blurred, as if gravity itself has smoothed its edges. This remnant, still known as NGC 7727, carries the unmistakable signs of disturbance. 2 galaxies once met here, bound by slow gravitational attraction, their shapes overlapping and dissolving over hundreds of millions of years. What remains now is not a perfect form, but a hybrid, luminous, uneven, and quietly unstable. Through telescopes, its structure tells the story of that long transformation. The outer arms are short, bent and fragmented, faintly glowing against the blackness. Dust bands curve inward at awkward angles. The central light is double-peaked, a hint that 2 nuclei still persist within a single envelope. The overall symmetry that defines most galaxies is absent. Instead, NGC 7727 seems to carry an impression of motion, as if its parts are still settling toward rest. The colour of its light reveals its age. Most of the visible glow comes from older yellow-white stars with only scattered blue knots, where new formation continues. The collision that created this system likely exhausted or scattered much of its gas, leaving behind little material for future generations of stars. Yet the traces that remain form gentle arcs, faint filaments that stretch outward in graceful curves. These are tidal relics, streams of stars torn from their orbits during the merger, now tracing long paths through the galactic halo. Even in their faintness, they are measurable reminders of the forces that shaped the system. The shape of each loop marks where gravity pulled most strongly, the invisible record of an encounter between two massive structures now fused into one. When astronomers first imaged this galaxy in high detail, they noted how its central region seemed oddly smooth, while its outskirts remained ragged. This difference tells of time and energy. The inner mass has already begun to relax into equilibrium, while the outer debris still follows elongated orbits far from any stable center. The process of merger is slow. Though the galaxies collided long ago, their remnants continue to mix, exchanging momentum, losing energy through friction and gravitational scattering. It will take hundreds of millions of years for the last irregularities to fade. In that span, dust lanes will disperse, stellar populations will even out, and the system will approach the quiet geometry of a single large elliptical galaxy. But for now it remains transitional, neither chaotic nor fully calm. At its core, the light is concentrated into two overlapping points. The brighter of these dominates, while the second sits slightly to one side like a small echo of the first. They are not separate galaxies anymore, but dense nuclear clusters drawn close by mutual gravity. Each likely shelters a massive black hole, remnants of the original galactic centers. Their separation, roughly 1,600 light-years, appears tiny compared with the galaxy's total diameter, but is enormous in absolute terms. Even so, the two are bound, moving through the same gravitational field destined eventually to merge. From afar, these centers appear as two beads of light within a broader diffuse core faintly veiled by dust. Their presence confirms the galaxy's origin, two former spirals now united. The surrounding stellar body supports this view. Streams of old stars radiate outward in broken arcs, wrapping around the galaxy like traces of a ripple frozen in time. Many of these stars have been stripped from their original orbits, thrown outward by the gravitational tides of the collision. Their paths now extend far beyond the main disk, forming a faint halo that grows more transparent with distance. This halo contains valuable information. By studying the motions of these stars, scientists can estimate how mass is distributed within the galaxy. The velocities show that dark matter still plays a role here, forming an extended invisible scaffold that holds the luminous material together. Without it, the outer stars would have escaped long ago. Though the merger's violence has long passed, its consequences remain visible in every part of the system. Gas clouds once compressed by the impact have since cooled, some collapsing into clusters of new stars, others dispersing entirely. Pockets of faint nebulae persist within the inner regions, but they are sparse and quiet. No large-scale spiral arms remain, only short fragments where gas density is still slightly higher. The galaxy's appearance in infrared wavelengths confirms this story. It glows weakly at those frequencies, meaning little warm dust remains. Star formation continues, but at modest rate compared to its earlier outburst period. Most of the energy now radiated comes from old stellar populations slowly fading into the red. In visible light, the galaxy's outer edge is delicate, its brightness falling off smoothly until it dissolves into the surrounding darkness. The faint extensions stretch outward for tens of thousands of light years, each one a pathway for wandering stars. These structures resemble the arms of other merger remnants such as those seen in the antennae, or the remnants of NGC 7252, though each case is unique in shape and scale. NGC 7277 appears to be further along the road towards stability, its once dramatic tails now thinned and dimmed. Time and gravity act as sculptors here, smoothing roughness without haste. From the perspective of the wider cosmic field, the galaxy's behavior is typical of such encounters. When two galaxies of comparable mass collide, they do not simply crash. Their stars pass through one another while their clouds of gas interact more directly. Friction, compression, and shock waves ignite bursts of new formation. Over long intervals, angular momentum redistributes, and what began as two separate disks eventually blends into one spheroidal body. The result is not destruction, but transformation, a single galaxy formed from two. The peculiar shape of NGC 7727 is simply one frame in that long sequence. It stands as evidence of the continuous cycle of merger and renewal that drives galactic evolution throughout the universe. The system's current calm can be deceptive. Even now its gravitational field carries echoes of past motion. Deep within stars move along orbits that twist and precess, responding to overlapping potentials. The light that reaches Earth captures only an instant in this slow ballet. Over millions of years these orbits will circularize, the core will condense, and the entire structure will smooth into a more regular profile. Observers in the far future would see a single large elliptical galaxy, with no visible trace of the collision that formed it. Only the deep gravitational record would remain preserved in the motion of its innermost stars and in the presence of the twin black holes yet to merge. For now, the remnant in Aquarius drifts through space with quiet dignity. Around it, the cosmic field glows with distant light, while within it the remnants of chaos turn gradually toward equilibrium. Its shape, though broken, is stable. Its light, though faint, endures. The two ancient cores at its heart remain hidden within that calm, their slow orbit continuing unseen. The galaxy's outer regions move gently like ripples fading across a vast invisible sea. Nothing here suggests urgency. The process that began with collision will end in quiet fusion, but that future lies far beyond any human horizon. In the present, NGC 772TF exists as it appears serene, irregular, and self-contained, a peculiar remnant suspended in the silent depth of Aquarius. Far beyond the luminous centre, faint rivers of starlight encircle the remnant. These tidal streams stretch across hundreds of thousands of light years, barely visible even in the deepest exposures, yet they form the most eloquent record of what the galaxy once endured. Each thread of light is a collection of stars torn from stable orbits during the ancient merger that gave rise to NGC 7727. Their paths now trace the gravitational memory of that encounter, curling outward in long, looping arcs. To the unaided eye, they vanish into the blackness, but to sensitive detectors they reveal an elegant geometry spirals that no longer rotate filaments, that twist around a core that has long since lost its symmetry. The sight is faint, but unmistakable. It is the signature of a collision that reshaped everything within this portion of the universe. When two galaxies meet, their stars seldom collide directly. Instead, gravity acts as an immense and invisible tide, pulling each stellar population toward the other. The result is not an explosion, but an unhurried distortion. Outer arms lengthen, disks stretch, and the farthest stars are flung into deep elliptical paths that wrap around both systems. Once the galaxies merge, these displaced stars remain bound to the new structure, moving through the halo as delicate threads of light. Over time, they fade, dispersing into a faint background that encases the main body like smoke around a dim flame. In NGC 7727, this process is well advanced. These streams are thin, their contrast low, but their presence defines the outermost region of the galaxy. Through them, the history of motion can still be read. The curvature of each stream suggests the direction from which the galaxy is approached. Some loop around the core, once others twice or more before fading. Their shape reveals how the collision unfolded, one galaxy likely larger and slower, the other lighter and more easily distorted. Their merger was not a single event, but a drawn-out sequence of passes, each one tightening their gravitational bond. The last approach tore away the remaining structure, mixing stars from both into a single chaotic field. Even now, those displaced stars continue their slow, bound motion, tracing a halo that extends far beyond the visible disk. Their faint arcs show that gravity, though invisible, leaves durable marks. Within these distant regions, the density of stars is low. A cubic light-year may contain only a handful of suns separated by immense darkness. Yet collectively they shape the halo that gives the remnant its diffuse outer glow. Most of these stars are ancient, drawn from the original spirals that collided. Their chemical compositions still bear the fingerprints of their parent galaxies. Spectral measurements show variations in metallicity, some rich in heavier elements, others poor. This patchwork hints at the original diversity of the two systems before their union. The merger blended them but did not erase all distinction. The outer halo remains a mixture of lineages, the fossil record of two once separate galaxies now joined under one gravitational field. The tidal features around NGC 7727 also reveal the influence of dark matter. Without its binding mass, the debris would have dispersed into intergalactic space long ago. Instead, the streams remain coherent, their orbits stable across millions of years. The unseen halo of dark matter acts as a vast container, its gravity keeping the outer structure intact while the luminous matter within continues to evolve. Astronomers studying these streams use them to infer the shape and size of that invisible framework. By mapping their motion, scientists can reconstruct the gravitational potential that governs the system. The results show that NGC 7727's dark halo extends well beyond the visible limits of its starlight, an immense bubble of mass within which the galaxy drifts. Closer to the core, where the density rises, the streams merge into a continuous glow. Here, tidal tails overlap and blur their individual lines, lost in a general haze. Within this zone, old clusters of stars orbit like small satellite survivors of the merger that remain gravitationally bound but distinct. Some of these clusters may once have been the nuclei of the original galaxy's satellites captured and retained as the main bodies collided. Their presence hints at the long complexity of galactic evolution. Each major galaxy often carries smaller companions, and during merger these are absorbed or cast outward into new paths. In this way, NGC 7727 has inherited not only the material of two large galaxies, but also fragments of smaller ones, their remnants hidden among its halo of light. From the perspective of deep space, these streams act like a clock. Their length and brightness indicate how long ago the merger occurred. Over hundreds of millions of years, the stars within each filament spread out their collective light, fading as they drift. The faintness of NGC 7727 streams suggests that the collision happened long ago, perhaps 1 billion years or more in the past. Yet the fact that they are still visible shows that the process of relaxation is not yet complete. The galaxy remains in transition, neither chaotic nor fully stable, its outer edges still carrying the slow echo of movement. Every particle of light in those filaments represents motion through gravity, a path drawn by the delicate balance between escape and return. Occasionally small patches of enhanced brightness appear along the tidal arms. These are stellar associations clusters that formed during the merger when gas was compressed by tidal shock. Most are now old and fading, but a few still contain young blue stars. Their presence demonstrates that the collision, though disruptive, also triggered renewal. Where gas clouds were crushed together, bursts of star formation occurred, creating new clusters that have since drifted outward along the same streams that once tore their parent material apart. Thus, within the apparent stillness of the halo, life continues in stellar form, a slow cycle of destruction and creation that leaves no sound, only faint light scattered across enormous distances. Seen in its entirety, the halo of NGC 7727 resembles a fragile shell. It marks the boundary between the galaxy and the deeper void, a limit where starlight dissolves into darkness. Beyond it, gravity weakens until the stars no longer remain bound. Some may already have escaped becoming wanderers between galaxies, carrying with them the chemical signatures of their origin. These intergalactic travelers move alone, tracing paths that may never intersect another system. Yet collectively they form part of the universe's diffuse light, the background glow that fills intercluster space. In that light lies the quiet residue of countless mergers like this one, each leaving its own pattern of debris. From this vantage, the galaxy's outer field appears to move at the slowest possible rhythm. The stars at the far edge complete an orbit over spans so vast that the entire history of humanity would fit within a single fraction of their path. Gravity continues to draw them inward, but time for them flows almost without motion. The tidal debris around NGC 7727 is more than structure. It is a record of time itself, a visible archive of events too slow to witness yet too large to forget. Within its delicate arcs, the memory of the merger endures, waiting for the day when the galaxy's two remaining cores will finally settle into one, and the last ripples of that distant union will fade into the quiet geometry of a single complete form. Far beyond the luminous streams where starlight thins into darkness lies the diffuse outer halo of the remnant galaxy. It is a region that stretches farther than the eye can follow, composed of scattered stars that drift in elongated paths around the hidden mass within. Here the galaxy dissolves into intergalactic space, its edges undefined and soft, its light a faint haze rather than a solid form. This is the realm of lost orbits where stars displaced by the ancient merger continue to move through enormous loops that take hundreds of millions of years to complete. They form no clear pattern, no discernible rotation, only a quiet suspension, as though time itself has slowed. The halo of NGC 7727 may be invisible to casual observation, but it holds the long after-image of the forces that once shaped the system. The stars that inhabit this region are old. Their colours lean toward the yellow and red of low-massive old suns that have burned steadily for billions of years. These are survivors pulled outward from their native disks during the collision. When the two parent galaxies passed through each other, their stars felt tidal forces strong enough to alter their trajectories, but not strong enough to unbind them completely. Many were launched into high-looping orbits, ascending far from the plane of the new system before curving back again. Others escaped entirely, moving beyond the reach of the galaxy's gravity. Those that remain form a tenuous population thinly spread across a vast volume of space. To an observer within that region, the night sky would appear sparse, with only a few points of light scattered across the black. Yet each of those stars carries with it the momentum and memory of the event that displaced it. The gravitational field here is delicate. The pull of the central mass weakens with distance, and the presence of dark matter becomes increasingly important. though unseen dark matter provides the glue that holds the halo together. Without it, these outer stars would drift away, escaping into the void between galaxies. The halo's slow rotation and extended structure confirm its existence. Luminous matter alone cannot account for the observed stability. The invisible component forms a spheroidal cloud much larger than the visible galaxy, stretching for hundreds of thousands of light years in every direction. The stars of the outer halo move within this unseen web, responding to its pull as they follow orbits that no longer align with any single plane. Their paths overlap and cross, creating a smooth distribution that appears uniform when viewed from afar. In this environment, collisions between stars are rare to the point of impossibility. The distances between them are so immense that each sun moves in isolation its nearest neighbour, perhaps several light years away. What binds them together is not proximity but shared motion through the gravitational field. The light from these remote stars blends into a faint continuous glow, detectable only with long exposure. Through sensitive instruments, this glow appears as a halo of soft light, surrounding the main body of NGC 7727, gradually fading until it merges with the darkness beyond. It marks the limit where the galaxy's influence ends and the intergalactic medium begins. Beyond that boundary, individual stars still occasionally drift outward, crossing the threshold between bound and unbound space. Once they pass it, they become part of the quiet background that fills the larger cosmic void. Within the halo, small star clusters also move along wide orbits. Some are remnants of the galaxy's original globular systems, while others may have formed during the merger itself. Each cluster contains hundreds of thousands of stars packed tightly together, glowing as compact points against the dim background. Their motion is slow but steady, tracing long ellipses around the galaxy's center. Over immense spans of time, these clusters act as test particles mapping the gravitational potential of the system. By studying their distribution, astronomers can infer how mass is spread through both the luminous and dark components. The results reveal a structure that extends far beyond what is visible, a shadowed architecture that defines the galaxy's true scale. The halo also preserves clues about the direction of rotation. Though the merger erased much of the ordered motion that once characterized the parent galaxies, faint traces remain. Some stars still follow coherent streams, their velocities aligned along certain axes. These are relics of the original angular momentum, diluted but not destroyed. They show that NGC 7727 did not form through random collapse, but through the meeting of systems that once had distinct spins. The merging of those motions produced the diffuse rotation, now observed in the outer regions, a slow drift rather than a rigid spin. It is motion measured in kilometers per second across light years of emptiness, imperceptible to any direct sense, yet continuous and exact. Radiation from the halo is faint but not uniform. Subtle color variations mark differences in the ages and compositions of its stars. Some patches contain slightly younger populations, likely formed when residual gas from the collision cooled and condensed in the outer regions. These stars are rare, scattered and short-lived compared with the older majority, but their presence adds texture to the halo's otherwise even light. In infrared images, they appear as gentle mottling across the diffuse glow. This complexity gives the outer halo its fragile beauty, a mosaic of faint colors stretched thin across the dark. The stillness of this environment can be misleading. Although the overall structure seems frozen, every star continues to move, responding to gravity with perfect obedience. Their orbits shift slowly through precession tracing paths that evolve over millions of years. Some stars will drift inward, drawn closer to the central mass. Others will climb higher, pulled outward by interactions with passing clusters, or faint perturbations in the gravitational field. Over time, these motions redistribute energy within the halo, gradually leading the system toward equilibrium. The process is invisible to the human eye, but fundamental to the galaxy's long-term stability. The halo acts as a reservoir of motion, absorbing and dispersing the residual energy of the merger. In the vast perspective of cosmic time, this region represents the galaxy's outermost memory. The collision that created NGC 7727 has long ended, but its effects continue to echo through the halo. Each star, each cluster, and each filament of light is part of that lingering resonance. Eventually, friction and scattering will smooth away the last irregularities, leaving only a uniform distribution of matter surrounding a stable core. When that time comes, the halo will still exist, but its connection to the event that formed it will be invisible. It will appear as the quiet envelope of an ordinary elliptical galaxy, indistinguishable from countless others that have followed the same path. For now, the halo remains a place of transition, a zone between motion and rest, between the galaxy's inner structure and the wider universe beyond. The stars that occupy it are wanderers bound but nearly free their paths, stretching far into the surrounding dark. From this distant vantage, the galaxy appears self-contained, yet its light merges gradually with the background of space, showing that no boundary in the cosmos is ever truly sharp. The outer halo of NGC 7727 is both part of the galaxy and part of the universe that holds it a quiet interface where gravity fades but never fully ends. It is here in the silence beyond the core that the scale of the system becomes clear. A fragile island of starlight adrift in an ocean, without shore, still governed by the faint and patient hand of gravity. Deeper within the remnant, the light grows warmer and denser, passing through regions veiled by thin layers of cosmic dust. The transition from the pale outskirts to this inner zone is gradual, yet the change in texture is unmistakable. The outer halo fades into a milky haze, and then almost imperceptibly, a faint pattern of absorption begins to appear. Dust lanes, born from the remnants of interstellar clouds, cross the inner regions like smoke trails frozen in motion. They are the debris of the merger's most turbulent stage, when gas clouds collided and compressed into filaments, then cooled and settled under the pull of gravity. These dark ribbons absorb and scatter starlight, softening the galaxy's inner glow and giving it the subdued tone that defines its present state. In the visible spectrum, they create irregular shadows that streak across the core, obscuring parts of the underlying structure. In infrared light, however, they reveal themselves fully glowing faintly with the warmth of countless microscopic grains heated by nearby stars. The dust is not evenly spread. It forms arcs, knots, and wisps distributed in patterns that hint at an underlying rotation. Some filaments curl inward toward the center, as if tracing the last surviving fragments of the spiral arms that once defined the parent galaxies. Others appear chaotic, suspended in overlapping layers without clear orientation. The composition of these grains is similar to that found in many other galaxies' silicates, carbon compounds, and tiny crystals coated with ice, each fragment less than 1,000th of a millimeter across. Collectively, they shape the visual character of the galaxy, turning brightness into glow, structure into atmosphere. Though their mass is small compared with the stars around them, their influence on the passage of light is profound. Through them, the galaxy gains texture, depth, and a sense of quiet opacity, as if its core were wrapped in a thin translucent veil. The presence of dust tells of gas, and where gas survives, new stars can form. Within the veiled interior, small knots of star formation persist, faint, but detectable in ultraviolet and hydrogen alpha emission. These regions are modest compared with the grand starburst events that accompany more violent mergers, yet they add a living rhythm to the otherwise aging system. The gas that fuels them has likely survived in pockets shielded from earlier turbulence. After the collision, much of the interstellar medium was stripped away or heated beyond recovery. What remains has cooled, forming small molecular clouds scattered through the central few thousand light-years. These clouds, dense enough to collapse under their own gravity, now give rise to clusters of young bright stars. Their light filters through the surrounding dust, creating a soft reddish glow that blends with the older stellar population. In some areas, the dust appears to form a faint disk flattened by slow rotation. Observations in the near-infrared suggest that this inner structure may still retain some organized motion, perhaps a remnant of one galaxy's original plane. Its alignment, however, is tilted relative to the larger body, a sign that the merger has not yet reached full equilibrium. The gravitational forces at play twist the material, bending and warping the disk as it processes around the center. Over time, friction and radiation pressure will disperse much of it, leaving behind only a trace of warmer dust and the metallic gas released by dying stars. For now, the veil remains substantial enough to mark the transition between the clear outer halo and the luminous bulge within. The colors in this region are subtle. In visible light, the inner dust lanes appear brownish against the pale yellow background of old stars. In infrared, they shine faintly red, warm to just a few tens of degrees above absolute zero. Within them, carbon molecules and silicate grains interact with starlight, absorbing high-energy photons and re-emitting them at longer wavelengths. The result is a quiet luminescence, an infrared whisper that outlines the galaxy's inner structure. Sensitive detectors aboard space-based observatories have traced this emission, mapping the flow of dust and gas across the central regions. The pattern resembles a web of filaments converging toward the nucleus, evidence of slow but persistent inward drift. Gas once scattered across vast distances now falls gently toward the core, feeding both the birth of stars and the eventual growth of the black holes that wait deeper inside. This inward flow is not uniform. Turbulence lingers from the collision, stirring the gas into eddies that spiral and fragment. Some regions are compressed enough to ignite new formation. Others are heated and dispersed by radiation from young stars or by shocks from supernovae. These competing processes create a fragile balance between destruction and renewal. The dust clouds shaped by magnetic fields and stellar winds twist into filaments that stretch across hundreds of light-years. Seen in silhouette, they resemble brushstrokes of shadow painted over the light of the galaxy itself. Within them, chemistry continues silently. Hydrogen combines into molecules, carbon forms chains and rings, ices condense onto grains. Every atom and molecule within these clouds contributes to the slow rebuilding of the galaxy's interior. As one moves closer to the center, the light becomes steadier. The chaotic filaments give way to a smoother glow as the density of stars increases. Here the dust begins to thin its particles, sublimated by radiation or swept away by gravitational tides. Yet faint traces persist, especially in the lanes that encircle the nucleus. These inner veils serve as the last visible reminder of the galaxy's gaseous past. They also act as screens that soften the glare from the crowded stellar core, allowing astronomers to glimpse its structure without saturation. Behind these screens, the light density rises sharply, signaling entry into the central bulge. The region as a whole radiates an atmosphere of calm, but this serenity conceals complex dynamics. Within, the dust gas and stars move on intersecting paths drawn by the combined gravity of the two massive centers still hidden inside. The motion is intricate, with orbits twisted and stretched by the overlapping gravitational wells. Over time, friction between gas streams will cause them to settle into a more regular configuration, forming perhaps a single rotating disk. Until then, the dust remains a tracer of transition, evidence of motion not yet resolved. Viewed in composite images, the veiled interior of NGC 77U7 glows like an ember seen through mist. The outer halo fades into it seamlessly, and the eye is drawn inward toward the warmer center, where the dust becomes most pronounced. There is no clear boundary, only a gradual deepening of light. The entire structure seems to hover between order and disorder, illuminated by stars that are both ancient and newly born. It is a region where time appears layered the old light of red giants, mingling with the sharp blue of young clusters, the scars of collision mingling with the quiet rhythm of renewal. This dust-filled heart marks the point where the galaxy begins to turn inward upon itself. Every filament, every faint glow is part of a long process of reorganization. The merger has left the system scarred but alive, and through the slow movement of gas and dust, a new balance emerges. The veil that hides the center is not simply an obstruction, but a stage of transformation. Within it, the past and future of the galaxy coexist, the remnants of destruction and the seeds of reconstruction woven together into one subdued light. The path ahead leads deeper toward regions where dust-thin starlight strengthens, and the true gravitational heart begins to reveal itself. Within the dusty interior, scattered reservoirs of molecular gas remain relics of the merger's turbulent past, yet still active in subtle ways. These pockets are fragile survivors clinging to stability amid the gravitational tides that continue to shape the galaxy. In most mergers of this kind, much of the cold gas is either consumed in starbursts or stripped away entirely, yet in this system a modest fraction endured. It collects in clumps and filaments several hundred light-years across, composed mainly of molecular hydrogen, too cold to emit visible light. To trace it, astronomers rely on the faint signature of carbon monoxide, a molecule that glows softly at millimeter wavelengths. Mapping that glow reveals the unseen structure of the gas threads, knots, and diffuse clouds arranged like a faint skeleton beneath the visible stars. In NGC 7727, the distribution of these regions is irregular, mirroring the fractured symmetry of the galaxy itself. The total amount of gas still present is small compared with what existed before the collision, yet it remains a vital element in the system's evolution. Each pocket serves as a potential cradle for new stars where gravity may eventually overcome internal pressure and trigger collapse. Within these clouds, temperature and density vary. Some are warm and diffuse, their molecules drifting without order. Others are cold and dense, their cores on the verge of condensation. The densest areas shield themselves from radiation with dust, allowing molecules to form and persist. Inside such environments, atomic hydrogen bonds into molecular pairs, carbon and oxygen unite to create carbon monoxide, and tiny grains of dust provide surfaces on which more complex chemistry unfolds. Although this process occurs slowly, it is continuous, turning simple gas into the building material of future stars. Star formation in this remnant is not concentrated in grand spiral arms, as it would be in a normal disk galaxy. Instead, it appears in isolated knots scattered throughout the central few thousand light-years. Each region forms a self-contained system, a miniature nebula of creation surrounded by older inactive stars. Observations in ultraviolet light and in the hydrogen alpha emission line reveal small clusters of hot young stars embedded within dusty cocoons. Their combined radiation carves cavities in the surrounding gas, creating bubbles of faintly glowing plasma. These pockets mark the last sparks of stellar birth in a galaxy that has largely settled into maturity. The overall rate of formation is low, perhaps only a few solar masses per year, but it is steady, sustained by the gas that continues to drift inward under gravity's quiet influence. The conditions that allow these regions to exist are a delicate balance of pressure, cooling, and gravitational compression. When gas from the merger was funneled inward, much of it was heated to high temperatures by shocks and turbulence. Over time, as the chaos subsided, some of that material cooled, losing energy, and settling into the denser layers now seen as molecular clouds. These remnants orbit the central mass in slowly decaying paths, colliding occasionally and merging into larger complexes. The collisions trigger local instabilities, compressing the gas and setting off small bursts of formation. In the absence of the large-scale rotational order once provided by spiral arms, this stochastic process defines the galaxy's ongoing regeneration. Infrared observations show that many of these regions are embedded within faint dust disks where gas dust and newly formed stars coexist. The young clusters produce intense radiation that heats the surrounding grains, causing them to shine at mid-infrared wavelengths. From space-based telescopes, these clusters appear as small, bright points scattered across a background of diffuse emission. Some lie near the central bulge, others along the inner lanes that trace the paths of infalling gas. Each represents a local equilibrium, an island of star formation surrounded by a sea of older stars that no longer create new light. In time, these clusters will disperse their stars, drifting outward to join the larger stellar population. Yet while they last, they give the galaxy a quiet pulse, a sign that even after collision and loss, the cycle of creation continues. The molecular gas also plays another role. It mediates the gradual feed-in of the black holes that lie deeper within. As gravity draws material inward, part of the gas loses angular momentum and drifts toward the center. Some of it may eventually reach the accretion zones around the two supermassive black holes, providing fuel for their slow growth. The process is inefficient and subtle, producing only faint signatures of energy, release occasional flares of X-rays or radio waves, rather than the blazing brilliance of an active galactic nucleus. These minor eruptions hint that the core is not entirely dormant, but for now the galaxy remains in a state of near rest. The gas that feeds the black holes also nourishes the final episodes of star formation, linking the fates of stars and gravity in a single cycle. Chemical composition offers further insight into the history of these clouds. Spectra reveal enriched material containing heavy elements forged in previous generations of stars. Iron oxygen and silicon are abundant evidence that the gas has been recycled many times through stellar life and death. Each supernova in the past contributed new elements which later condensed into dust and returned to the interstellar medium. The result is a chemically mature environment, fertile for new formation but limited in supply. Over the next hundreds of millions of years, this gas will continue to thin its molecules, consumed by new stars or expelled by stellar winds. When that happens, NGC 7727 will transition fully into an old red system, with little left but long-lived low-mass stars radiating gently into the dark. Within the faint molecular clouds, the cycle of collapse and birth unfolds almost imperceptibly. Gravity gathers the gas, pressure resists it, turbulence shapes it into filaments. At certain points, the balance tips and a fragment condenses into a dense core. As it collapses, it heats, igniting nuclear fusion and producing a star that will shine for billions of years. Around it, residual gas forms a thin disk where smaller bodies may someday arise. On cosmic scales, these details are small, yet they define the heartbeat of a galaxy. Each new star contributes to the gradual replenishment of the system's light, maintaining its luminosity even as older populations fade. Seen from afar, the central regions of NGC 7727 show subtle hints of this ongoing renewal. The glow of young clusters blends almost invisibly with the older background, their blue light softened by dust. The overall impression is one of quiet persistence rather than activity. Nothing here burns fiercely. Everything proceeds with restraint. The merger that once ignited starbursts of violent brilliance has long subsided into equilibrium. What remains are small sustained processes, molecular clouds, reforming stars, emerging radiation diffusing through the dust. The galaxy has entered a phase of calm reconstruction, where gravity, chemistry, and time act together with measured precision. In this balance lies the character of the remnant itself. The molecular gas, though limited, provides continuity between the chaos of collision and the stillness of maturity. It links the violent past to the serene present, allowing light to be reborn from the remnants of destruction. Within its cold depths, future stars wait in silence, their formation governed by forces too slow to witness, yet too constant to stop. Over millions of years, these pockets will fade, their gas spent, their clusters dispersed. The galaxy will grow older, quieter, and simpler. But for now, it breathes softly through these scattered reservoirs, a faint but enduring rhythm that continues beneath the veils of dust and light. At the heart of the galaxy lies a broad and luminous bulge, a dense concentration of old stars that dominates the remnant's inner structure. From the fading halo and veiled dust lanes, the light grows steadily stronger toward this core, reaching a smooth radiance that seems almost solid. The bulge extends for several thousand light years, a sphere of glowing matter that marks the galaxy's gravitational center. Here, the population of stars is overwhelmingly old yellow and red giants that have exhausted much of their hydrogen and now shine with steady, gentle light. They form a composite of the two galaxies that merged long ago, their orbits mixed and randomized by the violence of that encounter. Where once there were ordered disks and spiral arms, now there is only a spheroidal swarm, a vast sea of stellar motion without clear direction. The bulge of NGC 7727 is calm but dense, its stars separated by only fractions of a light year, its light uniform when seen from afar, yet filled with constant microscopic movement. The gravitational field in this region is intense, pulling every particle of dust and gas toward equilibrium. Stars here move quickly, completing orbits around the center in only a few million years. Their paths cross and weave in complex patterns, producing the overall impression of stability, even though each motion is individual and chaotic. Over long intervals, interactions between stars redistribute momentum, smoothing the system into a state of near-perfect symmetry. The bulge thus becomes the anchor of the entire galaxy, the region from which the rest of the structure gains its shape. In mergers such as this, bulges often serve as the enduring remnant of the event, outlasting the disks and arms that were once their defining features. NGC 7727's bulge reflects that history, a product of disorder refined into balance. The density of light near the center rises so sharply that it blurs into a continuous glow in most images. High-resolution instruments reveal countless unresolved points, each one a sun merging into an almost fluid brightness. The color leans toward warm gold, a sign of evolved stellar populations. Only in scattered regions does a faint trace of blue appear, evidence of the small pockets of young stars still forming from residual gas. These younger stars stand out sharply against the older backdrop, adding subtle complexity to the bulge's uniform hue. Yet they are temporary, soon to fade or merge indistinguishably into the surrounding sea of light. The overwhelming majority of the bulge's mass belongs to stars that are billions of years-old remnants of earlier galactic generations drawn inward over cosmic time. Dust in this inner region is minimal compared with the layers beyond. Most of it has been either consumed or cleared by radiation and gravitational compression. What remains drifts in faint filaments that encircle the nucleus, marking the last remnants of interstellar matter. These thin wisps absorb some of the light from behind, creating subtle variations in brightness that give the bulge texture. In infrared views, where dust glows faintly instead of blocking light, the central regions appear nearly transparent, revealing the uniform distribution of stars inside. The luminosity profile declines gradually with distance, following the pattern typical of elliptical systems. This smooth gradient confirms that the two galaxies have fully blended at the stellar level, their once separate populations now indistinguishable, except through precise measurement of their motions. Those motions tell a detailed story. Spectroscopic studies show that the stars in the bulge do not all move in the same direction. Rather, they exhibit a range of velocities, forming a pattern of partial rotation mixed with random movement. This kinematic blend is characteristic of merger remnants. The original angular momentum of the parent galaxies has not vanished, but has been redistributed throughout the new system. Some of it survives as a slow rotation around the central axis, while the rest has been converted into velocity dispersion, the random motions that give the bulge its stability. This combination creates a gravitational equilibrium in which the overall structure remains steady even though no single orbit is predictable. The result is a dynamic stillness where energy and motion exist in perfect statistical balance. Deep within this region, gravitational potential wells overlap, one belonging to the larger black hole and the other to its smaller companion. Though still separated by more than 1,000 light-years, their influence reaches far beyond their immediate surroundings. The stars of the bulge feel their combined pull, and many orbits are subtly elongated or twisted as a result. Over time, these interactions will continue to redistribute energy, slowly drawing the two black holes closer together. For now, their effects manifest only as gentle asymmetries, slight variations in velocity fields and density contours. Even these minor distortions, however, tell astronomers that the core is not static but alive with invisible motion. The temperature within the bulge is not measured in degrees, as it would be in gas or dust, but in the kinetic energy of stars. Each one moves at hundreds of kilometers per second relative to the others, creating a gravitational pressure that maintains the structure's shape. This internal motion acts like heat in a solid body. The faster the stars move, the more resistant the system is to collapse. Over billions of years, encounters between stars, though rare, gradually exchange energy, allowing some to drift outward, while others sink closer to the center. This slow process of dynamical relaxation helps maintain balance, ensuring that the bulge neither expands nor contracts significantly. It is a self-regulating mechanism governed entirely by gravity. The chemical composition of the bulge's stars further confirms its maturity. Spectral analysis shows a high abundance of heavy elements such as iron and magnesium, products of previous generations of supernova. These metals indicate that the bulge formed from material already enriched by long cycles of stellar evolution. The merger simply combined two such populations, producing an even more chemically complex whole. The resulting stars are luminous but age their fusions, proceeding slowly as they approach the final stages of life. Many will eventually shed their outer layers, forming planetary nebulae that briefly brighten the surrounding space before fading into white dwarfs. In this way, even the seemingly static bulge participates in the ongoing rhythm of change. From a distance, the bulge gives the galaxy its characteristic glow, a concentrated nucleus surrounded by faint outer light. It is what first draws the observer's eye, appearing as a steady beacon in an otherwise irregular shape. Yet what seems simple is built from countless individual motions, all finely balanced. The merging of the two galaxies has erased most visible traces of structure, but within the bulge the memory of that union endures in the random orientation of stars and the lingering asymmetry of light. These remnants of turbulence are subtle but persistent, woven into the dynamics of the system. In the larger story of NGC 7727, the bulge represents a middle ground between the quiet outer halo and the more active dual nucleus that lies deeper still. It is the zone of settlement where the chaos of collision has already transformed into equilibrium, but before the ultimate convergence of the two central black holes. Everything within it moves towards stability, yet the process remains incomplete. Over the next few 100 million years, gravity will continue its patient work, drawing energy inward, smoothing the last irregularities and preparing the galaxy for its next phase. For now, the bulge shines as a tranquil sphere of light, an enduring monument to the merger that created it, and the calm precursor to the hidden forces gathering in its depths. At the very center of the remnant lies the feature that defines its uniqueness: two distinct nuclei shining within a single envelope of stars. This is the core of NGC 7727, where the aftermath of collision has preserved the evidence of two once separate galaxies not yet fully merged. In visible light, these nuclei appear as two bright points embedded in a smooth glow, close enough to influence each other, yet still separated by about 1,600 light-years. Their presence was first suspected from irregularities in the galaxy's light profile, then confirmed through high-resolution imaging that resolved both peaks individually. The brighter nucleus occupies the approximate center of the galaxy's mass, while the fainter one sits slightly off-axis, surrounded by its own small swarm of stars. Together they form a binary core, the gravitational heart of the remnant and the silent stage for the long process of coalescence that lies ahead. The larger nucleus is a dense spheroidal cluster of old stars concentrated enough to appear almost featureless at normal magnification. It marks the location of the primary supermassive black hole, a body with a mass estimated near 150 million times that of the Sun. The surrounding stars orbit rapidly, their velocities revealing the presence of a gravitational well far deeper than their collective mass could produce alone. The smaller nucleus, less massive but still formidable, contains a black hole roughly 6 million solar masses in strength. It drifts through the stellar background like a companion satellite, carrying with it remnants of the smaller galaxy that once hosted it. Its own stellar cluster remains compact, showing that it has not yet been fully disrupted by the dominant gravitational field. The two cores, though, bound by the same galaxy, remain distinct two centers of mass orbiting within a common halo, slowly approaching under the influence of dynamical friction. Between them lies a region of disturbed starlight, a bridge of matter drawn out by tidal interaction. This luminous corridor contains stars stripped from both nuclei as they pass near one another. It is a faint but significant structure visible in deep exposures as a soft gradient connecting the two centers. Its presence confirms that energy is being exchanged, that the two black holes are no longer moving freely, but are beginning to spiral inward. The process is unimaginably slow, spanning hundreds of millions of years, yet its direction is certain. Each encounter between the smaller nucleus and the surrounding stellar field drains momentum from the pair, converting orbital motion into heat and gravitational waves that ripple faintly through the surrounding space. Over time, the separation will shrink until only one nucleus remains a single core marking the final union of both galaxies. The space between the two centers is filled with densely packed stars moving in complex orbits. Their paths are shaped by overlapping gravitational influences that cause them to twist and bend unpredictably. Some stars follow chaotic trajectories, occasionally passing close enough to one nucleus to be ejected from the region entirely. Others settle into elongated loops that carry them alternately around both centers, forming a faint hourglass pattern of motion. These interactions help to transfer energy away from the black holes, slowly tightening their mutual orbit. The process is known as dynamical friction. As each massive object moves through a field of stars, it creates a gravitational wake that exerts a drag force pulling it inward. Though imperceptible over short timescales, this mechanism ensures the eventual convergence of the pair. The presence of two nuclei transforms the surrounding light field. Instead of a single symmetrical brightness peak, the central glow of NGC 1727 shows a subtle elongation, a sign that the gravitational potential itself is asymmetric. The fainter nucleus appears slightly bluish, perhaps due to a small population of younger stars or a different metallicity inherited from its original host galaxy. The brighter nucleus radiates more evenly, dominated by older stellar populations typical of massive bulges. When viewed through instruments that can separate their spectra, the contrast between them becomes clear. The smaller core retains traces of a spiral origin, while the larger represents the smoother evolved population of a mature elliptical. In this way, the two nuclei embody the galaxy's dual heritage, the past lives of both progenitors, preserved side by side in the same stellar sea. X-ray and radio observations confirm that both nuclei contain active black holes, though neither shines with the intensity of a quasar. The radiation detected from their surroundings is weak and intermittent, suggesting that accretion is minimal. Small amounts of gas still fall inward, drawn from the remaining molecular reservoirs in the galaxy's interior. As it spirals down, the gas heats and emits faint X-rays, providing indirect evidence of the invisible engines at the cores. These emissions vary over time, flickering slightly as the flow of matter changes. For the larger nucleus, the signal is steadier, consistent with a dominant black hole already well settled into its environment. The smaller one shows more variability, perhaps, as its accretion disk forms and dissipates in response to tidal forces. The combined luminosity of the two remains modest, far below the threshold of an active galactic nucleus. The system has entered a quiescent phase where the drama of the merger continues not in light but in gravity. The geometry of this double core provides astronomers a glimpse into the stages of galactic evolution. Few systems are caught in this intermediate moment when two black holes are close enough to be bound but have not yet merged. NGC 7727 therefore serves as a laboratory for understanding the mechanisms that govern such unions. Its proximity, relatively close on cosmic scales, allows detailed study of the interaction. Observations reveal the faint distortions in stellar velocities that map the gravitational landscape between the nuclei. Computer models built from these data simulate how the pair will evolve orbital decay, driven first by dynamical friction, then by the scattering of stars and gas, and finally by the emission of low-frequency gravitational waves as the black holes approach their final collision. Within the galaxy, these processes occur silently. No visible motion betrays the forces at work. The two nuclei appear fixed in place, their separation unchanging to human eyes. Yet every million years the orbit tightens, the path shortens, and energy is lost to the surrounding stars. If one could observe the region over tens of millions of years, the smaller nucleus would be seen slowly spiraling inward, tracing a diminishing arc until the two centers converge. In that distant future, their merger will release a burst of gravitational radiation strong enough to ripple across the cosmos, though too faint to disturb the luminous calm of the galaxy that hosts it. For now, what can be seen is stillness, a quiet pair of lights nested within a golden halo suspended in equilibrium. Around them the bulge forms a smooth cocoon, its stars circulating with serene indifference. The dust and gas that once obscured the center now serve only as faint traces of structure, drifting through the gravitational currents between the two cores. Everything within this region seems to move toward resolution, yet the process remains far from complete. The two black holes continue their slow convergence unseen but inevitable, their orbits governed by laws that allow no haste. In this double nucleus, the story of the galaxy's creation remains visible. It is both the scar of its past and the promise of its future, a living record of how massive structures in the universe grow by union rather than creation from nothing. Each nucleus bears the legacy of its own galaxy, and together they illustrate the long continuity of cosmic evolution. To look upon them is to see a process that began billions of years ago and will not end for hundreds of millions more. Within the calm light of NGC 7727, the two centers shine quietly, marking a moment between destruction and unification, a pause in the endless rhythm of gravity that shapes the universe itself. The double nucleus of the remnant conceals what no telescope can directly see: two immense black holes whose combined gravity defines the entire heart of the system. Their presence is not inferred from light, but from motion, the speeds, directions, and dispersions of the stars and gas that orbit invisibly around them. Astronomers trace these hidden giants by measuring the subtle shifts in wavelength of the light from the surrounding region. Where stars move toward Earth, their light is slightly compressed. Where they recede, it is stretched. By mapping these Doppler shifts across the core, a field of motion emerges, a gravitational fingerprint that reveals the locations and masses of the unseen objects. In the case of NGC 772c7, this pattern shows two centers of attraction, each dominating a sphere of influence that overlaps with the other. One lies deeper, more massive and almost stationary within the broader bulge. The other is lighter, still wandering, yet its pull on nearby matter is unmistakable. Together they shape every orbit within thousands of light years. The larger of the pair occupies the dominant position. It anchors the galaxy's potential bending space so that stars move in steep elliptical orbits. The smaller black hole circles it, slowly completing a revolution, perhaps every few million years. Their gravitational fields interact, creating zones where stellar paths twist unpredictably. Some stars fall inward and are swallowed. Others are ejected outward at tremendous speeds, forming faint sprays of escaped light that fade into the halo. These high-velocity stars are direct evidence of the hidden giants. Their trajectories show that something far heavier than any cluster of stars resides within the core. By combining these observations with models of stellar motion, scientists estimate the mass of the main black hole at roughly 150 million times that of the Sun, and its companion at around 6 million. These figures, immense yet precise, define the scale of gravity within the galaxy. At such densities, ordinary physics gives way to the geometry of space-time. The black holes themselves emit no light, yet the material near them glows faintly as it accelerates inward. Dust and gas, drawn too close, form transient disks that radiate weakly in X-rays and radio waves before vanishing beyond the event horizon. These emissions are sporadic, reflecting the intermittent flow of material. The larger whole remains mostly quiet, its surroundings depleted after billions of years of slow consumption. The smaller one, still adjusting to its new orbit, captures occasional clouds of gas and flares, briefly before subsiding again. The signals are faint but measurable, allowing astronomers to confirm the presence of active accretion. What is seen today is not a dramatic display of cosmic violence, but a subdued, steady exchange, gravity, feeding slowly on the remnants of a galaxy's past. Around the black holes, the density of stars increases sharply. The innermost few hundred light-years contain a swarm of objects moving at velocities exceeding several hundred kilometers per second. Their motions trace the contours of invisible wells carved into the fabric of space. Each black hole holds a sphere of influence within which its gravity dominates over that of the surrounding stars. For the primary, this sphere extends for about 500 light-years. For the smaller, perhaps a fraction of that. Within these zones, stellar orbits are fast and eccentric. Many stars travel close to the event horizon, their paths deflected into elongated ellipses that precess with every revolution. Some are eventually torn apart by tidal forces, releasing bursts of radiation before disappearing into the darkness. These occasional disruptions provide another indirect signature of the hidden giants, brief flashes that mark their continuing influence on the matter around them. The motions of stars in the region are not random. Patterns emerge when mapped in detail: areas of compression, where velocities converge, zones of dispersion where they diverge. These patterns reveal the gravitational conversation between the two black holes as they tug at each other across space. The smaller one creates a localized distortion, a subtle ripple in the velocity field that shifts as it moves. Over time, this ripple migrates inward, its position changing as the orbit decays. Observing this motion across decades may eventually allow scientists to measure the rate of orbital decay, directly an extraordinary glimpse into one of the slowest processes in the universe. Simulations of such systems show how the black holes interact through their shared stellar environment. As they orbit, they scatter nearby stars, flinging them outward and absorbing angular momentum in return. This exchange acts like friction, causing the pair to draw closer. At first, dynamical friction dominates, driven by the collective gravity of the bulge. Later, as their separation shrinks, individual stellar encounters become more important, each one stealing a small portion of orbital energy. Eventually, when the distance between them is only a few light-years, the process will enter its final stage, governed by gravitational radiation. The two black holes will then spiral together, emitting waves that ripple through space at frequencies far below what current detectors can perceive. The final merger will release more energy in a few minutes than all the stars in the galaxy produce over centuries, yet at this distance it will be seen only as a quiet change, a transformation within silence. For now, however, everything proceeds with measured slowness. The region surrounding the pair is stable, its light steady. Stars orbit in their complex patterns, dust drifts through weak magnetic fields, and faint radiation seeps outward. The black holes remain hidden, their boundaries defined only by the absence of light. To the human mind, accustomed to events measured in hours or years, their motion seems frozen. But over the long timeline of galaxies, this is a period of transition, an interval between two states of being. The merger has brought the cause together, the future will bring their union. The present is the pause between these extremes, a still frame within a sequence that will continue long after every star now shining has dimmed. Even in this quiet state, the influence of the hidden giants extends far beyond the center. Their combined mass shapes the orbits of stars across the bulge, defines the stability of the dust lanes, and governs the slow inward drift of the remaining molecular gas. They act as the axis around which the entire system balances, an unseen center that gives the galaxy coherence. Without them, the structure would gradually disperse its stars, drifting apart over cosmic time. Instead, gravity binds the whole, ensuring that the remnants of the collision remain a single entity. The dual black holes, though invisible, are the architects of order within chaos. From Earth, the double nucleus appears calm, almost delicate. Nothing in its appearance suggests the tremendous forces concealed beneath. Yet within that light, billions of orbits intersect billions of gravitational calculations unfold every instant, and two singularities wait in patient motion. Their silence is deceptive, their influence is absolute. As they continue their slow dance, they reshape the galaxy at every scale, from the trajectories of stars to the faint arcs of dust, from the faint X-ray flicker of accretion to the hidden vibration of space-time itself. In tracing them, astronomers glimpse not only the fate of NGC 7727, but also the destiny of every large galaxy in the cosmos, for most harbour similar pairs waiting to merge. In this system, the hidden giants remain quiet for now, guardians of a stillness that is only temporary custodians of a process that will one day shake the universe itself. At the exact centre of the luminous remnant lies the deeper gravitational well of the primary black hole, the unseen structure that governs nearly every movement in its surrounding realm. Though no light emerges from its event horizon, its presence is recorded in the behaviour of the star's gas and dust that orbit invisibly within its sphere of influence. This sphere extends for several hundred light-years, encompassing millions of suns, each moving at speeds of hundreds of kilometres per second. To describe it is to map space itself distorted by gravity, where geometry bends and time slows. The black hole cannot be seen, yet the patterns it imposes are precise, measurable and unmistakable. It holds a mass roughly 150 million times that of the Sun, making it one of the more massive known in any galaxy of similar size. Within its reach, ordinary motion becomes extraordinary. Stars that might have once followed circular orbits now plunge inward, swing past the centre in tight arcs, and then rise outward again in long-stretched ellipses. The light from this region is smooth and golden, created by countless overlapping stars moving through paths that never intersect. Each orbit traces a different angle, a different velocity, a different plane, yet together they produce a seamless radiance. The effect is that of stillness, though every component is in motion. The gravitational potential here is deep but stable. Stars that venture too close accelerate sharply their velocities, betraying the immense mass hidden within. Observations made through integral field spectroscopy, where each pixel in an image records its own spectrum, reveal a distinct pattern of rotation and dispersion around the core. The velocity field curves smoothly, peaking near the centre, and declining outward exactly as predicted for a system dominated by a massive central object. This motion, not light, outlines the shape of the black hole's domain. The energy near the event horizon is immense, though mostly invisible. As small amounts of gas drift inward, they form a tenuous accretion flow heating to millions of degrees before crossing the boundary where escape becomes impossible. The radiation produced by this process is faint compared to the brightness of the surrounding stars, yet sensitive instruments detect it in X-rays and radio waves. It flickers irregularly, marking the feeding rhythm of the black hole. These flashes are modest, far less violent than those of active quasars, but they reveal that accretion never entirely ceases. Matter continues to fall inward at a slow, steady pace drawn by gravity that allows no rest. This process, though quiet, defines the long-term evolution of the core. The black hole grows incrementally, its mass increasing over millions of years, while the surrounding stars adjust to its pull. Closer to the event horizon, the laws of physics as understood on Earth lose their meaning. The curvature of space becomes extreme, and time itself passes more slowly relative to distant observers. Within a few light days of the center, gas whirls in near light-speed orbits, its thermal energy radiated away in brief flashes that vanish into darkness. This region, though infinitely small compared with the galaxy around it, commands control over hundreds of billions of stars. It is the pivot point of NGC 7727's structure, the reference from which every other orbit takes its measure. The gravitational influence extends outward, merging seamlessly with the combined potential of the galaxy's bulge and the distant halo. In this way, the black hole is both separate from and continuous with the larger system and invisible heart through which the galaxy breathes. The light that emerges from the stars nearest the center carries subtle signatures of their environment. Spectral lines broaden and shift, showing the speeds at which these stars move. By measuring those lines, astronomers derive not only velocities, but also the distribution of mass within the core. The results consistently indicate that no ordinary collection of stars could produce such motion. Only a compact object of enormous mass fits the data. In the case of NGC 7727, the central mass accounts for nearly 1% of the entire stellar mass of the galaxy, an unusually high proportion that testifies to the scale of its merger history. The collision that formed this system funneled large amounts of gas and stars toward the center, feeding the growth of the black hole and deepening its gravitational well. Over time, the region stabilized, but its memory of those events remains written in the kinematics of its stars. Despite its invisible nature, the primary black hole affects the galaxy far beyond its immediate neighborhood. It governs the rate at which the remaining gas can settle, the degree to which the smaller black hole can approach, and even the slow precession of the stellar bulge. The gravitational field acts as a regulator, aligning the motions of nearby material and smoothing the remnants of chaos left by the merger. The result is a central region that appears tranquil even while containing energies beyond comprehension. The heat radiation and magnetic fields generated near the black hole radiate outward, influencing the ionization state of the surrounding gas and shaping the faint filaments of dust that spiral into the core. Though the power of this influence diminishes with distance, its reach defines the structure of the entire inner galaxy. The balance between activity and quiescence in such a system is delicate. If new gas were to flow inward in quantity, the black hole could flare into a bright active phase, outshining the galaxy itself. But NGC 7727 appears to have passed beyond that stage. Most of the fuel from the merger has already been consumed or expelled. What remains drifts inward in sparse streams, producing only modest radiation. This subdued state may persist for hundreds of millions of years, until the final merger with the smaller black hole injects new energy into the system. Then, for a brief moment in cosmic terms, the galaxy's center will awaken, emitting a burst of radiation before settling once more into calm. The quiet appearance of the present therefore masks a future event of extraordinary scale. Even so, the black hole's gravitational dominion remains constant, immune to the fluctuations of its surroundings. It bends the orbits of stars like light around glass, focusing and guiding them through paths they cannot escape. Occasionally a star will stray too close and be torn apart by tidal forces its material, forming a temporary disk that glows for months before fading. Such events are rare but inevitable, each one a reminder that the serene light of the bulge hides regions of immense violence. For every star lost, countless others continue their steady revolutions, tracing patterns that have persisted for eons. The system as a whole is stable, its motion governed by a single unseen presence whose nature transcends matter and light. From a human vantage, this region can only be imagined through the evidence it leaves behind, a map of velocities, a pattern of faint emissions, a shadow cast not in light, but in gravity. Within that shadow lies the most massive object in the galaxy, the outcome of countless generations of collapse and merger. It anchors NGC 7727 against the pull of time and dispersal, holding the stars in their long orbits, while the universe continues to expand around them. Though silent and invisible, the larger black hole defines everything that the galaxy has become. Its gravity is the shape of permanence itself, the unbroken thread linking the chaotic past of collision to the calm and luminous present that now drifts quietly through Aquarius. Orbiting deep within the gravitational field of its massive neighbour, the smaller black hole moves through a sea of starlight and dust that it no longer controls. It is a survivor from one of the two galaxies that once collided to form this remnant, a remnant within a remnant carrying with it the faint memory of its origin. Its mass, though enormous by any measure, is modest, compared with that of the primary about 6 million times that of the Sun. Yet this smaller gravity well remains powerful enough to shape its immediate surroundings. It drags a small stellar cluster along its path, a compact envelope of older stars that continue to orbit the hidden core. Seen in high-resolution images, this envelope forms the fainter of the two nuclei, a discrete point of light slightly displaced from the center of the galaxy's brightness. Within it, the stars move rapidly, their velocities betraying the pull of the invisible mass at the center. Around this minor nucleus, faint streams of starlight extend, drawn out by the constant tug of the larger black hole nearby. The companion follows an elongated orbit that carries it through regions of differing density and brightness. As it travels, it interacts with the surrounding stars, producing ripples of motion that radiate through the inner bulge. Each pass through denser regions of the galaxy slows it slightly, draining a small amount of orbital energy. This gradual loss of momentum, known as dynamical friction, is the invisible mechanism by which the two black holes approach one another. The smaller object creates a gravitational wake in the stellar field behind it, pulling stars slightly out of place. Their collective attraction tugs backward on the companion, causing it to sink ever closer toward the central mass. Over tens or hundreds of millions of years, this subtle process will bring the two black holes into tighter orbit, preparing them for the eventual stage where gravitational waves will take over. At present, the companion still maintains a considerable distance, roughly 1,600 light-years from the main core. From a cosmic perspective, this separation is close enough to classify the pair as bound, yet far enough that their individual spheres of influence remain distinct. The smaller black hole governs the motion of perhaps a few million stars within a radius of several hundred light-years. Beyond that boundary, the gravitational pull of the larger dominates. Between the two lies a region of transition filled with orbits that are neither stable around one center nor the other. Stars in this zone move along twisted paths, alternating allegiance between both giants. Some are captured and later released, others are flung outward entirely. The interplay of these motions produces the subtle asymmetry visible in the galaxy's inner light, a faint elongation that hints at the ongoing gravitational struggle beneath. The stellar cluster surrounding the smaller black hole is a relic of its original galaxy's nucleus. Its stars are older than those in the outer bulge, rich in heavy elements and arranged in a steep density gradient. At its very center, velocities reach extraordinary values, hundreds of kilometers per second, indicating a concentrated mass too great to be explained by stars alone. The companion black hole sits quietly within, invisible but dominant. Its accretion of gas is minimal. What material drifts near it is sparse, left over from the merger's dissipating clouds. Occasionally a filament of gas passes close enough to ignite brief accretion, releasing weak X-ray and radio flares before fading. These episodes are small and transient, more like echoes of former activity than new events. Most of the time, the companion remains dark, its presence marked only by the gravity that holds its cluster together. The orbit of the smaller black hole carries it through the dense stellar environment of the bulge, where countless interactions subtly alter its path. Each close passage with another star transfers a minute fraction of energy, a process repeated endlessly across millions of encounters. The cumulative effect is profound. The companion slows, its orbit decays, and its trajectory becomes more circular. Over time, the cluster that accompanies it will be stripped away, its stars scattered into the background of the larger galaxy. Already, some of these stars can be traced in elongated trails that extend behind the moving nucleus, faint threads of light marking its passage. Eventually, the cluster itself will dissolve entirely, leaving only the black hole to continue inward alone. When that moment arrives, its motion will be determined solely by the deeper gravity of the primary. Within its own small sphere of influence, the companion's gravity continues to shape the motion of gas and dust. The remaining molecular clouds near it form irregular rings and arcs distorted by tidal forces. These structures hint at the same processes that once governed full galaxies, now compressed into a much smaller scale. Occasionally, as the companion passes near regions of higher gas density, tidal interactions compress the material, sparking brief flashes of new star formation. These events are rare but visible in ultraviolet light as faint transient knots. They serve as reminders that even within the approach toward final merger creation persists. Gravity's destructive power also generates new order, each collapse giving birth to more light. The smaller black hole's journey is slow but relentless. It traces a path that loops around the main core, oscillating slightly as it moves through regions of varying density. Each orbit takes millions of years to complete, yet with every revolution its pericenter, the point of closest approach, shifts inward. Simulations suggest that once the separation falls below a few hundred light-years, the rate of decay will increase rapidly. At that stage, interactions with the surrounding stars will become more efficient at extracting energy from the orbit. Eventually, when the two black holes reach a distance of only a few light-years, gravitational radiation will dominate, carrying away energy in the form of ripples through space-time. The final coalescence, though silent, invisible light, will send waves across the universe that instruments of the future may one day detect. For now, however, the smaller companion remains distinct, a faint nucleus, moving within the brighter glow of the galaxy's center. From Earth, its light is subtle, almost lost within the surrounding brilliance. Yet its movement can be mapped through variations in velocity across the core. The lines of stellar motion bend around it, curving slightly where its gravity alters the flow. In this way, its path can be traced even without direct sight. It is a moving weight within a field of light, an invisible traveler gradually surrendering to the greater mass that waits ahead. The energy it loses becomes the shaping force of the entire system, redistributing momentum and stabilizing the galaxy as a whole. The story of the lesser companion is one of endurance and inevitability. It represents the final remnant of an entire galaxy drawn into another, the last independent fragment of a vanished world. Its orbit is not a solitary fate, but part of a larger narrative that repeats throughout the cosmos. Every massive galaxy likely carries a similar history where smaller systems merge and their black holes sink inward to join the larger. In NGC 77227, this process unfolds with exemplary clarity, the smaller hole moving patiently through starlight, the larger waiting with silent gravity. Together they form a system in perfect slow motion, a record of how the universe builds structure through union rather than destruction. Seen from afar, the companion is merely a dim point within a luminous haze. Yet within that point lies the memory of another galaxy, the echo of a collision long past and the future seed of a single, far greater heart that will one day form at the centre of this quiet remnant in Aquarius. Within the inner few thousand light-years of the galaxy, the two black holes and their surrounding stars move in a slow, intricate dance, governed by gravity alone. It is a performance without sound or visible motion, yet every particle within this region participates in its rhythm. The larger black hole sits near the dynamical centre, massive enough to distort the local gravitational field. The smaller companion traces a looping path around it, losing energy with each pass as it interacts with the sea of stars and the faint remains of gas that still linger in the bulge. To human senses, this motion is imperceptible. To the universe, it is one of its most fundamental acts. The process transforms the energy of orbital motion into heat, and scattering, converting chaos into order with extraordinary patience. Each revolution of the smaller nucleus takes millions of years, but gravity keeps time, perfectly ensuring that every movement leads toward eventual convergence. The region between the two black holes is filled with dense stellar populations moving at high velocity. Each star responds not to one source of gravity, but to the combined field of both. As they orbit, they cross invisible boundary zones where the attraction of one black hole yields to the other. These crossings produce a phenomenon called three-body interaction, in which a passing star can exchange energy with the binary pair. In some encounters, a star gains velocity and is ejected from the system, entirely cast into the outer halo as a hypervelocity object. In others, the star loses energy, transferring it to the black holes and driving them slightly closer together. Over billions of such interactions, the average result is orbital decay. The two black holes spiral inward by infinitesimal degrees, their momentum dissipated into the galaxy itself. The stars, meanwhile, carry away the record of those exchanges in their altered orbits, forming diffuse patterns of motion that can still be traced in the surrounding light. This slow tightening is further enhanced by the presence of residual gas and dust in the inner regions. Though the galaxy's collision consumed most of its interstellar medium, thin filaments remain drifting through the gravitational field. As these clouds pass near the binary pair, they experience tidal compression and shear, losing angular momentum and sinking inward. The friction between gas particles converts motion into heat, and that heat radiates away, allowing the material to settle into new configurations. Some of it feeds the black holes, directly falling into the deep potential wells and releasing faint X-rays as it does. Other portions simply redistribute mass within the core, thickening the dense stellar envelope that surrounds both nuclei. In every case, the effect is the same. The orbit of the smaller black hole decays a little faster, its path drawing tighter around the larger one. From a distance, this invisible process manifests as subtle asymmetry in the galaxy's brightness. The central light is slightly elongated along the axis joining the two black holes, and the distribution of velocities around it shows a corresponding gradient. This elongation is not a fixed feature, but a dynamic one, changing slowly as the orbit evolves. Over the course of hundreds of millions of years, the two bodies will pass through several configurations: wide binary, close binary, and finally coalescence. Each stage modifies the shape of the stellar field, carving new structures that mirror the flow of energy through the system. The stars act as tracers of this process, their motions revealing the underlying mechanics of gravity in action. Inside this gravitational arena, time behaves differently. Close to the black holes, where curvature of space is strong, the flow of time slows relative to the wider universe. A photon emitted from near the event horizon loses energy climbing out of the deep gravitational potential its wavelength stretched into redder tones. From Earth, this redshift appears as a subtle softening of light from the inner core. It is not caused by dust or distance, but by gravity itself bending the path and energy of light. The effect is small, yet it is measurable, providing one of the most direct pieces of evidence for the presence of massive compact objects at the galaxy's heart. The surrounding bulge acts as both audience and participant in this cosmic choreography. Its stars respond collectively to the shifting mass distribution at the center, their velocities adjusting as the pair of black holes move. As energy is transferred outward, the bulge slowly expands, becoming slightly puffier and more diffuse. The central density decreases while the velocity dispersion rises, ensuring that the total energy of the system remains conserved. In the long term, these changes will transform the galaxy's profile, rounding its shape and erasing any residual asymmetry from the merger. The process will not produce visible changes in any human timescale, but the physics unfolds with precision, step by step, orbit by orbit. The smaller black hole's orbit is not perfectly circular. It oscillates in an elongated path, sometimes drawing closer to the primary, sometimes retreating. At each close approach, tidal forces peak, producing temporary surges of radiation, as gas and dust are compressed between the two gravitational fields. These surges are faint but detectable in X-ray and radio wavelengths. They reveal the phases of the orbit, allowing astronomers to model the motion of the binary pair, even though they cannot see the black holes directly. As the orbit decays, these bursts will become less frequent but more powerful, marking the approach of the final spiral stage. For now, they remain rare events, quiet signals in the background of the galaxy's otherwise steady light. The dynamics of the two black holes influence the structure of their environment in complex ways. Around them, dense star clusters move in resonant orbits that can remain stable for billions of years. These resonances act like gravitational corridors guiding the flow of matter through the core. Outside them, stars with misaligned orbits experience irregular perturbations that slowly scatter them into the outer halo. In this way, the binary pair acts as a pump, transferring energy from its own orbit into the random motions of the galaxy's stars. This exchange is the mechanism by which large-scale stability emerges from small-scale motion. Over immense timescales, the entire system relaxes, achieving the smooth luminosity profile seen in old elliptical galaxies. It is tempting to imagine such a scene as static, but in truth it is dynamic equilibrium, a constant reshaping that happens too slowly for any observer to perceive directly. Even the faintest shift in orbital phase or the smallest gravitational scattering event contributes to the evolution of the system. The dance of gravity proceeds with a patience that dwarfs any human concept of time. In the future, the two black holes will continue this slow approach until they orbit within just a few light years of each other. Then the final act will begin when gravitational radiation, tiny ripples in the fabric of space, becomes strong enough to carry away energy faster than stars or gas can absorb it. The spiral will accelerate, culminating in the merger of two singularities into one. For now, the galaxy remains tranquil. Its light spreads smoothly, its core glows steadily, and its invisible actors move without sound or haste. The dance continues unseen, a process written only in equations and inferred from the measured motions of starlight. Yet this unseen motion defines the destiny of the system. It is the silent heartbeat of NGC 7727, a rhythm kept not by sound or light, but by the relentless pull of gravity shaping matter and time into the form of a single, slow-turning galaxy, adrift in Aquarius. Deeper within the galaxy's center lies the region where the two gravitational spheres of the black holes overlap, forming a single intricate domain of motion. It is here within a few hundred light-years of the double nucleus that the full complexity of the system reveals itself. The gravitational field is no longer dominated by one center or the other, but shared between both, creating a landscape of potential wells that curve, twist, and merge. Every star in this region moves under the influence of both black holes, its orbit a precise response to the shifting geometry of space. The stars do not form a simple cluster or disk, but a dynamically mixed population, some bound tightly to one black hole, others to both, and many following chaotic paths that change with every pass. The result is a core that seems stable when viewed from afar, but inside is filled with endless silent motion. The stellar density here is extreme. Within each cubic light-year, hundreds of stars orbit at velocities of hundreds of kilometers per second. Their light merges into a smooth golden glow, but hidden in that light are patterns of subtle asymmetry, slight shifts in brightness and color that reveal zones of compression and void. These variations record the unseen orbits of the twin black holes and the slow reshaping of the inner system. No star moves in a perfectly regular path. Gravitational tides stretch their orbits, scattering some outward into the bulge, while capturing others into closer loops. Every motion is part of a vast exchange of energy, a transfer that steadily drives the pair inward. Even the background of gas and dust responds to this dance, forming faint streams that spiral toward the center, guided by forces that never rest. The balance of forces in this region is delicate. The two black holes are bound together, but their shared system is constantly disturbed by the stars that wander through it. Each close encounter changes the distribution of energy, causing the black holes to lose a trace of momentum, while the passing stars are flung outward. The combined effect of countless such interactions creates a slow but steady contraction of the binary's orbit. The process is invisible on human timescales, yet relentless, measured not in years or centuries, but in tens of millions of revolutions. In this way, the binary core acts as a gravitational engine, converting ordered orbital motion into the random kinetic energy of the surrounding stars. The galaxy itself becomes the absorber of that energy, its inner bulge expanding slightly as the black holes sink deeper into union. Inside this crowded environment, collisions between stars are rare but not impossible. Occasionally, two bodies pass close enough to interact gravitationally, distorting each other's paths or merging into a single more massive star. Such mergers create short-lived bursts of blue light that stand out against the red and yellow of the older population. These flashes fade quickly, but they are reminders that even in the quietest corners of the cosmos, change is constant. The black holes themselves remain invisible, yet their influence governs every event. They act as silent conductors, coordinating the slow exchange of motion and mass that will eventually fuse them into one. The gas that remains in this region flows along curved channels shaped by the overlapping gravitational wells. These flows are faint but complex, forming spirals that thread through the stellar core like invisible rivers. As gas clouds intersect, they compress heat and sometimes fragment, creating small pockets of star formation, even within the dense heart of the galaxy. These newborn stars live fast and die young, their radiation helping to illuminate the central region. In infrared wavelengths, they appear as specks of light scattered among the older stars, marking places where gas has surrendered its energy to gravity. The existence of these pockets shows that the core, though dominated by ancient stars and dark mass, still holds the capacity for renewal. Within the innermost few light years, the structure of the binary core becomes even more intricate. The smaller black hole's orbit begins to align with the central plane of the surrounding stars, forming what astronomers call a hard binary, an orbital pair so tightly bound that it can no longer be separated by normal gravitational encounters. At this stage, most of the stars that cross their path are ejected outward, carrying away energy and angular momentum. The ejections produce no visible traces beyond subtle changes in the velocity field, but they accelerate the inward spiral of the two black holes. The core adjusts in response, redistributing its mass as stars are lost and new ones drift inward from the bulge. Slowly, the entire system begins to reconfigure itself around a single deepening center of gravity. The physical scales within this region are difficult to imagine. The combined gravitational field of the two black holes extends over distances comparable to the orbit of entire star clusters, yet the event horizons themselves remain smaller than the solar system. Between these extremes lies a continuum of motion stars orbiting in years, gas clouds in centuries, black holes in millions of years. Time flows differently depending on where it is measured. To a star near the edge of the bulge, the core seems frozen unchanging. To a particle near the horizon, everything moves with unbearable speed. This contrast defines the character of the binary core, a place where scale dissolves and every measure of motion depends on perspective. The radiation escaping from the region is faint but continuous. It carries the combined signatures of starlight-heated dust and weak accretion. Spectroscopic analysis reveals lines broadened by motion and reddened by gravity. Each photon stretches slightly as it climbs out of the deep potential well. The spectrum forms a soft continuum lacking the sharp peaks of more active systems. This indicates that NGC 727's central engine is quiescent, releasing only a fraction of the energy available to it. Yet this stillness is deceptive. The same forces that now appear dormant are slowly preparing the conditions for a future outburst, when the two black holes merge and release gravitational energy far beyond any visible radiation. The calm seen today is the precursor to that distant event, a balance held on the edge of immense transformation. In the meantime, the binary core continues its patient work. Stars circulate gas drifts inward, and the separation between the black holes diminishes imperceptibly. The galaxy around them remains luminous and serene, unaware of the colossal tension building within its heart. From the outside, the core appears as a single point of light. Only precise instruments reveal its dual nature. Within that point, space and time fold around masses so dense that even light cannot escape. The orbits of stars in this region trace invisible geometry, curved not by chance, but by the deep equations that govern gravity itself. The binary core is the living boundary between stability and collapse, between the visible universe and the domain where light ends. Eventually, as the orbit tightens beyond the reach of ordinary gravitational interactions, a new phase will begin. The black holes will move so close that their space-time distortions overlap completely, forming a continuous horizon. Long before that moment, the surrounding stars will have adjusted their motions, reshaped to orbit a single gravitational center. The galaxy will appear calm, its light unbroken, its inner symmetry restored. Yet at the smallest scales beneath the apparent stillness, the final spiral will proceed. Energy will flow outward in the form of gravitational waves, ripples in the structure of the universe itself, carrying away the last remnants of motion. When the merger is complete, there will be no flash, no explosion, only a slight deepening of the galaxy's central potential. The new single black hole will settle into equilibrium, and the core will once again appear motionless. The transformation will have ended exactly as it began, in silence within light that hides more than it reveals. As the slow gravitational spiral continues, the separation between the two black holes diminishes to just a few dozen light years. The binary system now moves as one structure, a pair of singularities enclosed within a common envelope of stars and gas that orbits their shared center of mass. each revolution brings them slightly closer, the decay of their orbit accelerated by every encounter with the dense stellar field. This is the threshold where gravitational radiation begins to play a measurable role, carrying away energy in the form of waves that stretch and compress the very fabric of space. Though these ripples are faint far beyond any detection by human instruments today, they are real, spreading outward in all directions. With every emission, the orbit tightens a fraction more, and the system takes another step toward unification. Nothing within this region moves quickly by human standards, yet every motion is inexorably aligned toward one final outcome. In this stage, the dynamics of the surrounding stars change dramatically. Those that pass too close to the pair are ejected outward at extraordinary speeds, gaining enough velocity to leave the galaxy altogether. These escaping stars carry with them the orbital energy of the binary, a process that further reduces the distance between the black holes. Each ejection is invisible to the eye, yet over millions of years the cumulative effect becomes profound. The core gradually clears itself of stars, leaving a shallow depression in density known as a stellar cusp. Around this hollow region, the remaining stars orbit in elongated paths, their movements synchronized by the combined gravity of the approaching pair. The structure becomes simpler and more symmetrical as the final merger draws near. The chaos of interaction gives way to the quiet of convergence, and the light from the central few hundred light-years grows smoother, its irregularities erased by time. The flow of gas through this region follows similar patterns. Tidal forces stretch the remaining molecular clouds into thin filaments that spiral inward along the gravitational gradient. These filaments collide shock and heat, producing brief flashes of infrared radiation before dispersing into the void. A small fraction of this material is captured by the black holes themselves, forming miniature accretion disks that orbit each one before being torn apart by tidal shear. As they merge, the two disks will interact their rotation axes, tilting and twisting, as magnetic fields reconnect in sudden bursts of energy. In theory, such interactions could produce a final flare, an electromagnetic echo of the merger visible across millions of light-years. Whether this will happen in NGC 7727 is uncertain, but the conditions for it are slowly assembling. For now, the system remains mostly dark, its power hidden within the mathematics of space-time. To the galaxy at large, this event will pass unnoticed. The stars of the bulge will continue their steady orbits, and the outer halo will remain unperturbed. The scale of the forces involved is immense, but so is the size of the system. Energy released by the merger will dissipate as gravitational waves, not light, and the galaxy's luminous structure will appear unchanged. Yet within the core, the transformation will be absolute. Two horizons will merge into one, their masses combined, their spins aligned into a single stable configuration. The resulting black hole will be slightly less massive than the sum of its parts, the difference radiated away as pure gravitational energy. For a brief instant, space itself will vibrate, carrying that signal outward at the speed of light. When those waves reach distant worlds, they will stretch and contract space by less than the width of an atom, but their existence will testify to an event of unimaginable scale. The timeline for this process is vast. Astronomers estimate that it will take hundreds of millions of years before the final coalescence occurs, though the precise rate depends on the density of stars and gas in the central region. If a new influx of material were to fall inward, perhaps from a captured dwarf galaxy, or a stream of intergalactic gas, the merger could accelerate the additional mass, hastening the decay. If instead the core remains depleted, the orbit could linger in near stasis for eons. Gravity allows no shortcuts. The slow rhythm of loss continues until the remaining distance is small enough for radiation to dominate completely. When that stage begins, the spiral quickens dramatically. The final approach may last only a few thousand years, the last instant, in a process that began when the universe itself was younger than it is now by nearly 1 billion years. In the moments before coalescence, the two black holes will orbit each other many times per second, their velocities approaching a significant fraction of the speed of light. The energy contained in that motion will be released through gravitational waves, each cycle radiating outward with greater intensity. As the orbit tightens further, the frequency of the waves will increase, producing a crescendo that peaks at the instant the horizons merge. In that final act, space will ring like a struck bell, emitting waves that travel outward for eternity. No explosion will mark the event, no flash of light, only a subtle oscillation of the universe itself. Afterward, the single merged black hole will recoil slightly, carrying the memory of its asymmetric birth as a drift through the stellar core. The recoil velocity may be hundreds of kilometers per second, enough to displace it from the exact center, before gravity draws it slowly back again. For the stars that survive near the new singularity, nothing will appear different. They will continue their orbits, responding only to the combined mass now concentrated within one gravitational horizon. The transition from two centers to one will smooth the potential field, simplifying their paths. The surrounding dust and gas will reorganize, forming a new equilibrium structure, perhaps a faint torus of warm material encircling the core. Over time, this structure will cool dim and eventually fade, leaving behind a single luminous nucleus, indistinguishable from that of a normal elliptical galaxy. The evidence of the merger will remain only in the motions of the outer stars and in the faint gravitational wave signature traveling outward through space. The system will have completed its transformation from a chaotic collision to a unified quiescent whole. In the wider cosmic context, such events are neither rare nor common. They are the natural consequence of galactic evolution. Every large galaxy is thought to harbour a supermassive black hole at its centre, and galaxies themselves grow through mergers. Each union repeats the same slow choreography that NGC 77227 now enacts: approach, collision, duality, and finally synthesis. The light we see from this galaxy is an ancient frame in that universal sequence, a single snapshot of a process that defines how structure in the universe matures. In this sense, NGC 772 is both specific and archetypal, its quiet core a living example of the continuity that binds matter and time. As the orbit shrinks and the two black holes close their final gap, the forces that shape the galaxy reach their culmination. Energy, mass, and momentum converge into one. The larger structure remains serene, its glow unchanged, but deep within the final merger waits. It will happen silently, unseen by any eye, yet its effects will travel across the cosmos long after the galaxy itself has evolved into something new. The two black holes, once distant giants from separate galaxies, will cease to exist as individuals and become a single perfect object, the enduring gravitational heart of NGC 727, a centre of stillness formed not from destruction, but from the slow, inevitable uniting of all that gravity holds. After the long spiral of billions of orbits, the two black holes finally merge into one. The transition, invisible in light, alters the entire gravitational structure of the galaxy. Within a span of only moments, two distinct wells of space-time collapse into a single, deeper one. The event horizon of the new black hole expands slightly. As the combined mass settles into equilibrium, its spin stabilizing under the conservation of angular momentum. A faint tremor of gravitational energy escapes across the cosmos, passing through clusters, nebulae, and the dark matter filaments that span intergalactic space. Long after, the waves will continue outward, crossing distant galaxies, and eventually fading into the universal background. The merger itself leaves behind no visible trace. From a distance, the core looks as it always has, a calm sphere of light at the centre of a faintly distorted galaxy, but its inner geometry has changed forever. In the new configuration, the surrounding stars adjust their orbits. Those that once circled one nucleus now respond to a single gravitational centre. The velocity field of the galaxy simplifies its chaotic ripples, smoothing into coherent motion. Within a few million years, the last asymmetries from the merger will be erased. The stellar cusp, previously hollowed out by the black hole's interactions, begins to refill as stars drift inward under the pull of the unified core. The bulge stabilizes its light profile, settling into the classic form of an elliptical galaxy. Observers on distant worlds would see a smooth, symmetric glow, its brightness, peaking gently at the center, its structure revealing nothing of the tremendous transformation that occurred there. Only the dynamics of its inner stars would hint at the immense mass hidden beneath. The new black hole's properties are defined by its ancestry. Its mass is slightly less than the sum of its predecessors, the difference radiated away as gravitational energy during the merger. Its spin, determined by the vector sum of the two original rotations, likely approaches the maximum possible for a stable object. This rapid rotation distorts the surrounding space, dragging it into motion and shaping the paths of nearby matter. Around the event horizon, the frame-dragging effect causes particles and light to orbit in warped trajectories. The result is a faint but measurable twisting of the geometry around the core, a phenomenon that reveals itself through the polarization of emitted radiation. These details are not visible directly, but can be inferred from models and from the subtle signatures embedded in X-ray and radio data. Through them, the hidden structure of the galaxy's heart becomes knowable, even though it can never be seen. In the aftermath of the merger, the supply of gas and dust in the immediate region is greatly reduced. The gravitational violence of the event clears out much of the surrounding material, either consuming it or flinging it outward. What remains forms a faint torus of hot plasma that encircles the black hole at a distance of a few light years. As it cools, this plasma emits soft X-rays and radio waves, the only lasting visible consequence of the union. These emissions will fade over time as the torus dissipates and the core returns to its long dormant phase. The galaxy will enter a new equilibrium, its center quieter than before, its structure more unified. For the first time in perhaps a billion years, NGC 7727 will exist as a single stable entity, its internal tensions resolved. The surrounding stars continue to move, tracing graceful arcs that intersect and overlap but never collide. Some of them, perturbed by the sudden deepening of the gravitational potential, are flung outward in broad hyperbolic paths. These become intergalactic wanderers travelling for eternity through empty space. Others fall inward, their orbits tightened by the increased mass of the central object. Over time, the distribution of energy among the stars restores equilibrium. The galaxy's luminosity softens but remains steady, a field of warm light diffused across tens of thousands of light years. To external observers, it is the image of serenity, a mature elliptical galaxy with a faint halo and a bright, well-defined core. The remnants of its spiral arms, tidal streams and dust lanes will fade as the last traces of its merger history are erased by time. The new black hole, now the undisputed ruler of the galaxy, acts as an anchor for all remaining matter. Its gravitational reach defines the orbits of every star within several thousand light years. It will continue to grow slowly, accreting what little gas remains, and occasionally consuming a passing star or compact object, Each such event releases a brief flare of high-energy radiation before fading back into quiet. These episodes will punctuate the long calm of the galaxy's future, brief reminders of the power that still resides at its center. Yet they will be rare, separated by millions of years of stillness. The prevailing state will be one of balanced mass distributed in harmony with gravity energy, radiated slowly, entropy rising imperceptibly. In the long future, as the galaxy ages and its stars exhaust their fuel, NGC 7727 will grow fainter. Its bright young populations will vanish, replaced by red dwarfs and dying giants. White dwarfs will accumulate in the halo neutron stars, and stellar mass black holes will drift silently through the bulge, and the great central singularity will remain at the heart, unseen but eternal. The two black holes that once orbited separately will by then be impossible to distinguish. Their individual histories will have merged into a single smooth gravitational field. If intelligent observers were to study the system billions of years hence, they would see only a quiet elliptical galaxy, unaware that its center was once a battlefield of colliding masses. The record of that event will survive only in the ripples of space-time still traveling outward through the cosmos, each one carrying a tiny imprint of NGC 77227's transformation. In this way, the galaxy completes its evolution. What began as two independent spirals rich in gas and structure has become one smooth, luminous sphere. The process that joined the merger turbulence, duality and coalescence has ended in perfect order. The violence that once defined the system has subsided into balance. The stars move in predictable paths, the black hole rests in quiet dominion, and the energy of the past is preserved in motion too slow to see. The galaxy is neither dead nor alive. It is complete, its processes continuing only as echoes of earlier ages. The two black holes, once distinct, now exist as a single equation written into the geometry of space itself. Nothing more will happen quickly here. The rhythm has slowed to the pace of eternity. From a human distance, the entire story appears as a still image, a faint elliptical glow, its center calm, its edges diffuse, its light travelling 89 million years to reach Earth. Yet within that light lies a history of collision, transformation and unity. NGC 777 now drifts quietly through Aquarius, its twin hearts joined into one. Gravity, the oldest force in the universe, has done its work completely, drawing chaos into order, motion into rest, and many into one. The galaxy remains luminous and unhurried, its hidden core a single horizon, where the memory of two black holes endures as one continuous presence, timeless, silent, and complete.